It is indeed a pleasure to come to Singapore, as I have on numerous occasions. This is going to be a rather peculiar talk, I think. I had two goals in trying to start it, and now I know how I would proceed if I were to do such a thing again. It was only by searching the internet a few days ago that I discovered that virtually everything that Charles put down on paper is available at the Stanford University Library. And there was something I was looking for, his course on time series, which I never completed. I only took a lecture or two, that I thought it would be very interesting to review in detail. But be that as it may, I decided that what I would try to do is, and this is what a very personal view means, I would review some of his less well-known, perhaps, papers, certainly not the two areas that he thinks are his primary contributions, and see why we regard him as just an incredible genius who was overflowing with ideas, but was still sort of reluctant to put them down on paper and discuss them. Although he would certainly discuss them with you personally if you ever went and asked him about them. In preparing this, I've not given any list of references. There are two published interviews with Charles, and I think they're both very interesting. One is in Statistical Science, and that's the one that's, I think, very easily accessible. Somewhat less accessible one is Professor Leong of the mathematics department here, who, on behalf of the IMS, interviewed a number of visitors. And I found his interview extremely revealing about the way Charles thinks about mathematics, statistics, and scientific problems. And I'll try to remember to mention a few of these as we go along. So, to some extent, this is historical. One of the things that Charles is asked by Leong is, what are his most important contributions? And he lists foremost his contributions to probability theory, which will be the entire theme next week. He lists his work on the inadmissibility of a multivariate normal mean, which he first published in 1956 as his second major contribution. And then he says, some people tell me that my 1956 paper on adaptive estimation, but that paper is filled with mistakes. Now, if Peter Bickel or some of the other invitees had been able to come this week, I wouldn't even begin to talk about that subject, and I'm going to give a very superficial description of it anyway. But I think that that's a wonderful paper. It appears next to his inadmissibility paper in the Third Berkeley Symposium, and it began 40 years of continuous research by some of the most outstanding mathematical statisticians in the field. But I want to begin with, now what did I do? I left my pointer here. I want to begin with the problem that Charles discussed twice before 1950. The first time was his thesis, and is very well known. It's reprinted as a short session of problems in Layman's book on testing statistical hypotheses. But then he published an abstract in Econometrica in 1949 that, I think because it was an abstract that he never developed, probably didn't have the influence it might have, but the problem that he set was actively involved in a large number of people in the 1950s and 60s and even into the 70s. And this is the problem. We take independent, normally distributed observations. They have an unknown mean mu, an unknown variance sigma squared, or perhaps it could even be known. we want to estimate mu by a confidence interval so that the length of the confidence interval can be prescribed. And here it's given as, here it's given as 2W. Here's the notation. X bar is the average, Sn squared is the sample variance. And what Stein said in 1945, which became his thesis, was you could do this with a two-stage procedure. But in 1949, he considered a purely sequential procedure. And this was his procedure, which was extremely ingenious. And we let Z alpha be the right percentile of the normal distribution. And if sigma happened to be known, if we take the smallest integer exceeding this quantity and just compute what the normal confidence interval would be, it would achieve our goal of a confidence interval of width at most 2W. But since if we don't know sigma, Stein's suggestion was just to sample until it appears that this inequality is satisfied. This inequality where we plug in the sample standard deviation squared, so it's sample variance. And so this is his formal procedure, which is actually much more sophisticated than what I've just said, but it's sampling until the sample variance is less than or equal to some sequence of constants, and it just comes directly from this, except that this AN is to be 1 plus a constant minus a constant over n plus little o of 1 over n, and A0 should have the form of 3 minus a mysterious constant that Stein knew in his head what it was, but I'm sorry, he knew what it was conceptually. He never computed it. Plus this, and then we would achieve what we wanted, not just to first order, not just 1 minus alpha, but the second order term in an asymptotic expansion. He would have killed it by the proper choice of A sub n. That's why I bothered to write this as 0 times n0 to the minus 1 power. You kill that second order constant, so it should be a very accurate approximation. And this is the expected sample size, which is your target sample size, plus a little bit, plus a remainder. Now, it turns out that this problem was generated a great deal of research. In my view, and this was a very ingenious paper, but there's this mysterious constant rho that's not specifically identified. And what it amounts to is the amount by which this inequality is violated on average when the stopping occurs. And the person who I actually identified what that constant should be was Anscombe, who in 1953, and he references 3 papers by Stein, but none of them is this abstract. So I think that Anscombe's operating more or less without knowing what Stein had done. And he addresses the same problem, but he also identifies the constant rho, which he computes by solving a Wiener-Hopf integral equation. And he solves it numerically. Now, for the next 12 years, there's, I think, essentially no activity in this area. Then Chow and Robbins in 1965 dropped the hypothesis that the x's are normally distributed, but they only considered the first order asymptotics, which is a much, much simpler problem. And they showed that you could rigorously do what Stein and Anscombe were trying to do, except that they both had a second order asymptotic theory. Chow and Robbins only had a first order asymptotic theory. But the theory was so much simpler that everybody and his brother rushed in and said, well, we can do it for this problem, or we can do it for that problem. I'm going to come back to another problem later, which was not addressed immediately. But I do want to say that the definitive solution of this problem was due to Woodruff in 1977, who gave a complete mathematically rigorous development using what has come to be called nonlinear renewal theory, which was developed with other motivation in mind, but also statistical motivation, by Woodruff in 2 papers and by Lai and me in 2 slightly later papers. Okay, so let's drop that subject for a minute and go to the paper that I referred to, the 3rd Berkeley Symposium paper, which began the 40-year effort to study adaptive estimation. I believe the final word, although I'm not quite clear on this complete history, is due to Ad van der Vaart in his book on asymptotic statistical theory, the final chapter. And it's van der Vaart's birthday party that is one of the competitors of this meeting that takes a number of people to Leiden, the Netherlands, rather than here. So the problem is to provide a fully efficient estimator of a test statistic for a finite dimensional parameter in the presence of an infinite dimensional nuisance parameter. There are 2 parts of Stein's paper, both I think very, very clever. In the first part, he asks, what would this mean if we were talking about only a finite dimensional nuisance parameter? And he derives a matrix equation that shows when adaptive estimation occurs. And then he gives an asymptotic computation that indicates how one can obtain an asymptotically efficient test of the center of symmetry of an unknown symmetric distribution. And I might say that one of the questions that Professor Leong addresses to Charles Stein was, which is more important, computation or concepts in thinking about statistics? And Charles first says, oh, that's a difficult question. Both are important, but I guess I'm stronger in concept. But if you look at some of his papers, his paper on estimation of the multivariate normal mean, or if you look at the conditional distribution that he computes in this paper, you find that he is quite capable of doing as hard computations as anybody in the field. Now, let me just mention his matrix equation because, well, it has a personal interest for me for reasons that I'm going to show you later, and that was part of the personal aspect of learning this work. The problem is, suppose we have, now this is a finite dimensional problem. We have theta partitioned as a parameter of interest, theta 1, and then a theta 2 and a theta 3. So this is partitioned into a 3x3 block matrix. These can be vectors. We're interested in testing a hypothesis or estimating theta 1, and ordinarily when these parameters are unknown, the asymptotic variance of the maximum likelihood estimator of theta 1 will be increased by the presence of these nuisance parameters. Now, in Stein asked the question, well, okay, let's concede that if we estimate theta 2, we increase the variance because some of the variability of the estimate of theta 2 goes into our variance of theta 1 hat. But what would it mean to say that theta 3 does not contribute anything to the variance of theta 1 hat? And that's his matrix equation. He shows that estimating theta 3 does not affect the asymptotic variance if this condition is satisfied with the partitioned matrix. J13 is equal to J12, J22 inverse, J23. And his proof is algebraic. He just writes down the equations that have to be satisfied and solves them. Here's a simple statistical proof that I only stumbled on when I was sitting on the airplane and didn't have anything else to do for 15 hours. And I put my computer up above and somehow didn't want to get it down. Well, it was running low on electricity, was part of the problem. Stein's condition is the same as saying if we regress the score statistic for L for theta 1 on theta 2. And that means we take the conditional expectation of theta 1 considered as asymptotically normal, given theta 2, and that's the conditional expectation. If that is uncorrelated with theta 3, then theta 3 is not going to cost us anything in our estimate of in our estimation of theta 1. And that's sort of intuitively obvious. And if you write down what that means, it's precisely Stein's condition. Now, where am I? Okay. Now, it turns out that Fang Xiao and I are working on a problem that we've been working on because of my slowness for a year now, which leads to the same matrix equation, but not expecting it to have this structure, we did the computation in a very complicated way. So here's the model. dy is some given function, and think of mu of s as just being a constant, or mu plus alpha plus beta s, some simple parametric regression. And then there's something that upsets the regression. The upset occurs at the time t, and it's reflected by the shape of the function f, and there is an autoregressive element, and then a Brownian motion, white noise. So f is a positive kernel, for example, and I give some examples. If f is just the indicator that s is greater than 0, then this indicates a change point of size xc at the position t. If it's the indicator of an interval, then it's a change point where the process goes up, then comes back down, delta units later. A symmetric positive probability density function is Worsley's model for fMRI scans. And the positive part function is actually the one that Fang Xiao and I are spending most of our time on. So it just changes the slope of a regression but in a continuous way. It changes the derivative, so there's a jump in the derivative, but not in the function itself. And I'm going to assume that sigma is known, n equals 1. So the parameters of interest are these confounded parameters, xc and t. So this is an irregular problem, because if xc is 0, then t can't be defined. But let's just look at it as a function, how we would test xc equal to 0 with a fixed value of t. If we compute the efficient score for testing xc equals 0, it's this. I take the derivative of the log likelihood with respect to xc, set xc equal to 0, and theta equal to the maximum likelihood estimators under the assumption that xc is equal to 0. What we computed when we found this was that the variance of the numerator of our statistic, which can be expanded this way, that's just standard likelihood theory, expanded by, in effect, regressing this log likelihood on that log likelihood, and partition these things accordingly. And what we found was that, before we realized it, was that this variance doesn't depend on rho, the autoregressive parameter. And the reason it doesn't depend on rho is precisely Stein's equation, or the rewriting Stein's equation that I gave. However, we didn't expect that, so our original proof involved writing this information matrix and inverting it. And with alpha and beta in the problem, it's a 3x3 matrix. It was painful to invert it, at least painful for me. And it could be very, very simple if we had known to expect the result. Okay, so let's pass on to the Efron-Stein inequality. This is a wonderful inequality that's motivated by the notion of a jackknife, and I'm not clear how Efron and Stein interacted on this, But it says the following. If I take a function of independent random variables, virtually any function, but it has to be in L2, because I'm going to compute a variance, I define E sub I of z this way, and then what Effort and Stein proved, and E upper I of z is the expected value of z where I integrate out z sub I holding all the other variables fixed. And that, of course, is related to the idea of the jackknife, which is that you take out one variable at a time and average the function that you have left and use that as an estimate, use that in a variance formula as an estimate of the variance. That's the jackknife estimate of variance. And what they proved is that the variance of z is upper bounded by this expression, which is, as I say, if you interpret this thing in terms of the jackknife, it's the jackknife estimate of variance. Their proof relied on an ANOVA decomposition. So they basically wrote, or what you could call also U-statistic decomposition. You decompose this nonlinear function into a set of linear approximations. First order linear approximations, second order interactions, third order interactions, fourth order interactions, on down as far as it goes, till you get to the last nth order interaction. And then you compute. The book by Boucheron, Lugosi, and Massart has what has to be two very beautiful and very simple proofs, much improving on the Effort and Stein thing, but leaving behind its statistical origin, interpreting it purely as a probability result. They notice that that this is Doomb's martingale. You decompose z minus its expected value, which is this with I equals 1. You decompose z into this martingale, or z minus its expectation, as this martingale, the Doob martingale, and you make the observation that if you first integrate out z sub I holding all the other variables fixed, and then condition on the variable z1 to zi, it's the same as conditioning on the variable z1 to zi minus 1 and integrating out everything else. You do that, you write an expression for the variance, you use Jensen's inequality, and you're finished. It's really one line. But Boucheron, Lugosi, and Massart also show the wide variety of applications of this, including Poincare inequalities, the function of bounded differences theorem attributed to the guy from Oxford whose name I never remember, and the Rademacher averages. So this is widely used one way or another in machine learning. And this might be appropriate to mention another point that Stein makes in one of his interviews. He's asked whether statistics and probability are closely related or whether they're two different subjects. And he said, well, certainly in statistics, we use probability theory, but my use of it is rather straightforward. I just compute and use some probability theory to do the computations, but I think of them as really being two different subjects. Here is a wonderful example of how they should be thought of as the same subject. And I think, well, I'm going to come to another example of that same form where I think they really, and well, let me say, when I thought about how it could be that I could sit across the hall from Charles for 20 years and never, not never, but rarely talk to him. To some extent, it was that dichotomy. I do think of statistics and probability as being the same subject and have always looked for problems that I thought were interesting statistically that had some element of probability in them. And he thinks differently about that. And there's some other differences too that we have that, to my disadvantage certainly, prevented a richer interaction than the few times we did talk. But let me go on to one more subject, which is the likelihood principle. In 1974 in JRSSB, he published a short note containing an example designed to illustrate a serious flaw in the likelihood principle, the idea that everything that you want to do statistically should be based directly on the likelihood function. Now, he gives a very elegant example, and the thrust of his example is basically to show that the likelihood principle would lead you to declare that a parameter was outside of a confidence interval very often. And in fact, Charles never said formally, I really like the idea of confidence intervals, but when he came to talk about foundations, and he did this also in his paper on fiducial inference, both the likelihood principle and fiducial inference, in his view, failed because they gave you something that wasn't consistent with a confidence interval. Now, I want to say a little bit more about this problem, but let me also say that, well, no, okay, we'll come back to that maybe. So, while he wrote down the example just as here's a probability density function, he admits at the end of the article, the last paragraph, that he wrote down that density function thinking about this problem. We have independent normally distributed random variables with mean, mu, and unit variance, and we look at the sum of the observations and the sequential stopping rule the first time that the absolute Sn is greater than or equal to b times the square root of n. So this, in some sense, circles back to his very early work. It's just that there's a different problem, a different stopping rule. So the log likelihood function, standardized by taking out the log likelihood for mean 0, is this. Its maximum value is this, and according to our stopping rule, it's about equal to b squared. So the maximum log likelihood contains essentially no information about mu. It's the same, it's roughly the same for all values that you observe. And so how can it really provide information about mu? Okay, that's in some sense, although as I say, written quite differently in terms of a different log likelihood, that's his argument. But I would like to point out that this stopping rule is the natural solution of a problem or the natural simple-minded solution. Maybe I'm going to draw something on the board. So the idea is we plot Sn against n, we compare Sn to this parabola, and we stop the first time our random walk leaves this parabola, and that's our data. St and T and St, T should come first, and St. Now, if the mean is close to 0, this will occur eventually, but it'll occur largely because of chance fluctuations, not because of drift. However, if mu is far from 0, it will occur because of the drift. So in one case you get information about the size of the drift, in the other case you don't get much information except that it's close to 0. But if we ask for another kind of fixed width confidence interval, and in this case the confidence should be proportional. If we say, what would be how could we give a confidence interval for mu, assuming it's not 0, that says that the width of the confidence interval is no more than a small proportion of the actual value of mu. And if we imagine that mu is known at the same time we imagine it's unknown, contradiction in terms, of course, we could achieve what we want by taking n0 greater than or equal to this. And now this stopping rule merely is of the same philosophy as Stein's 1949 paper. We sample until when we put in an estimator for mu, it appears that this is satisfied. And that's this stopping rule. If we use Anscombe's theorem to justify the asymptotic normality of this, then we obtain essentially the desired confidence interval, providing epsilon is small and mu is not too small. Mu is too small, you drift way out here and you don't get much information at all. Now, let me just tell a small personal anecdote. Last year I taught, I think maybe for the first time, our statistical consulting class. We have a class where students sign up to do statistical consulting. They consult only for internal university people. This is not a money-making proposition. Nobody from outside the university. And then there's a discussion one afternoon a week when people interact with problems they faced, and usually the discussion centers around, well, what's this guy driving at anyway? Is this a well-formulated statistical problem? If so, what can we say? Now, it turns out that one time when I was sitting there, somebody said, the problem that was posed to us is how do we find a confidence interval for mu with prescribed proportional accuracy? And I almost jumped out of my skin because I had never seen anybody ask that question. But it also turns out that it is the subject of my first PhD student in about 1968, Arthur Nadish. Spent his career at IBM, Yorktown Heights. So I could tell him the answer. Now, I never found out who it was that asked the question, but I think I know, because I think I know where this is a natural question. In simulations in operations research, one typically runs into problems when one's operating, say, with a queuing system that's close to instability, and then a large sample size is required. The mean is typically large, but it takes a large sample size to estimate it, and asking, can we estimate it with proportional accuracy is a perfectly natural question. And my conjecture is that that's where this question came from, but I didn't bother to follow up and find out. But usually when I'm sitting in this room, the students can address each other's questions much more clearly than I can. So I was very pleased that at least once I could say, here is the answer, and you can find it in my PhD student's dissertation. Now, let me say a little bit more about this problem, because in another sense, this is the reason that Charles and I, although we both are of an age where you might think that we come from the same intellectual tradition, we didn't. Stein was a student of Abraham Wald. Wald was working on his book on decision theory, and Stein took decision theory very seriously throughout his life. When I started graduate school at Columbia University, which had been where Wald taught, this was still pretty much the attitude, and I thought, this is a beautiful subject. This is what I want to learn. But then at some point, we parted ways, and I think we parted ways maybe partly due to this book by Armitage, which involved sequential analysis, which I was very keen on, with a sort of a decision theoretic flavor, which was the flavor that Robbins was interested in, my advisor, that Chernoff was interested in, my sort of first colleague at Stanford. But Armitage posed the problem in a way that just sort of escaped decision theoretic formulation. But it was an applied problem. And I sort of said to myself, well, I can either continue to talk about decision theory as mathematical statistics, or I can try to communicate with applied statisticians. And I would like to try to communicate with applied statisticians. And so this is one of those results. Maybe my most successful in this direction. So Armitage suggested in a problem of testing whether mu is 0 or not, to stop with the minimum of t and m. So now I add one more line. We go out here to time m. Let's put it there. And if we haven't stopped before then, we call it quits, and then we accept the hypothesis that mu is 0. And there are modifications of this, but let's just stick with this form of it. Now we ask the question, can we give a confidence interval for mu? And I want to give it in a way that's not the same that I discussed just a moment ago. And the idea is the following. Our data is a pair, t and st, and we orient the boundary this way. Stopping here suggests a certain value for mu. Stopping here suggests a larger value for mu because it reflects a larger slope in getting to where we stopped. Can we use that orientation to define a confidence interval? And that would certainly be a violation of the likelihood principle. And we did that. And I managed to find an old program that does some version of that. And this is just a numerical example to show that if your stopping time is too large with this boundary b times the square root of t, you're not going to estimate a lower confidence bound close enough to 0. So if you use the asymptotic normality of st, that is what was on the preceding slide, you get, for this particular example, b equals 3, t equals 100, and st is just right on the border. A 95% lower confidence bound is 0.14, but in fact, this is cooked up to be such that this occurs not because of the drift, but because of the fluctuations in Sn, and the bound on this other method that I think I gave a publication date for is about 0.07. So near 0, when mu is near 0, you get a very much a biased estimate by using the other method. Nevertheless, I find a very interesting method when mu is not close to 0. Okay. Now I'd like to make a few random remarks. Other things that I read in the process for doing this that told me something I hadn't known before. For example, in Stein's approach to the central limit theorem, a great deal is made out of the fact that a standard normal random variable satisfies this equation. This is related to his treatment of the central limit theorem. It's also related to his discussion of inadmissibility of the maximum likelihood estimator, the multivariate normal mean. I had assumed that since the multivariate normal mean was discussed more than 10 years before the central limit theorem, that he actually knew this inequality, this identity, and used it in 1956 or maybe 1966, but he didn't. This, I think, first appears in print in a statistics paper discussing admissibility in 1981, roughly 10 years after. So he, one way or another, he came up with this equality for discussing probability theory, and then said, aha, and this will work to understand statistics as well. Now, the analogous identity for the Poisson approximation, I'm pretty sure does come from a statistical calculation, because he was well aware of Robbins' 1956 paper on the empirical Bayes method, where Robbins does not write down this equality, but it's close enough that it could be exactly this equality. And Stein was aware of that paper, and in fact gives Robbins some credit for convincing him that maybe the multivariate normal mean was not admissible, since the natural way to think about it was it must be. How could it be inadmissible? But okay, so there is this analogous equation for the Poisson distribution, and I think that what is not the exact equation, but something very close to that equation, shows up in Robbins' 56 paper and then in later papers by Robbins also. In his, now my last, well, a couple more random remarks. In his monograph on approximate computation of expectations, where he develops both the normal approximation and the Poisson approximation, and does it very elegantly, there are two orphan chapters, I would call them, chapters 5 and 6. They are problems, they are calculations that he starts and just drops for whatever reason. The first one deals with large deviations, and the second one with local limit theorems. And both of them are approached, and for densities, for random variables with densities. And in fact, one of the discussions that I remember having with him was, I asked him whether his method could be used to find probabilities of large deviations. I think he already knew the answer. The answer is probably pretty close to yes, but he has to make a number of heuristic assumptions to do it. And he never comes back to that problem. And the same thing is true of the local limit theorem. Now, for random variables with smooth distributions, these two are actually very closely related, because the standard approach is the paper by Bahadur and Ranga-Rao in 1961, I think, where you first do for large deviations, you first do an exponential tilting of the distribution, and then you apply local limit theorems. But as far as I know, these problems, at least at this level, have been left as orphans by Stein, and now I will invite Adrian to contradict me, because he certainly has written on the local limit theorem using Stein's method in a paper, and I guess it was Andrew was a co-author of that paper. No? It's not for sums of ID random variables, it's for some other process. And they should tell us what the true story, what the true status of these chapters that I've called orphans is. And then finally, and I invite Ian or anyone else who would like to contradict me here. I've said that Stein seems to have liked the idea of confidence intervals because he uses them in his discussions of what's wrong with fiducial inference and in his discussion of what's wrong with the likelihood principle. He wrote at least two papers. One is a 1962 paper which appears as a discussion paper in JRSS and is entitled Confidence Intervals from Multivariate Normal Mean. He gives so many different confidence intervals, you can't figure out if he likes one of them better than the others, and I don't think he does. 1962 was soon enough after 1956 that although this was a discussion paper, everybody discusses the 56 paper in admissibility. They don't really grapple with the question of how can this be used to find confidence intervals. In 1981, which is the paper when he returns to inadmissibility, he has a final section where he proposes a still different method for finding confidence intervals, and he gives some references to related research of others. But I certainly came away with the impression that he was not happy with any of these, and it certainly, if that's correct, it certainly would be a very interesting open problem to try to sort through some of these ideas and see if some of them have merit above the others. And with that, I'll thank you for your attention and ask for questions. Ian? Uh-huh. Mm-hmm. Okay. Well, as we all know, who knew Charles even a little bit, he was an extremely modest person and very generous, although also with exceedingly high standards. So if he thought he knew the answer to something, he didn't tolerate another answer. But by and large, questions where he didn't know the answer, and he was quite free to admit that he didn't know the answer, he was very generous in attributing ideas to others. And this may be such an example. Mm-hmm. Yeah. Okay. Uh-huh. Yeah, yeah. Mm-hmm. Mm-hmm. Well, I guess I looked for that kind of analysis in some of his decision theoretic papers, and didn't find it. But I didn't look. Maybe I didn't look late enough, because I'm sure that he was in his description, he said many times, I've only used Bayesian methods as a technical tool, and given how this duality works in simple cases like just estimating a location parameter, for example, it's certainly natural to think that he would ask it in a tough problem, and I don't know how it turned out because I never found that publication. Well, as I said at the beginning, just by random internet search, I became aware that Charles Jr., Charles' son, deposited Charles' papers in the Stanford University libraries in the historical archive. And you can see everything that he left as notes. Now, I thought I was actually going to find everything I wanted from Percy, who was a great fan of Charles and talked to him a great deal, and was sort of disappointed that I couldn't find, that Percy never knew, for example, that Charles had taught a course on time series. That was one of the things I was looking for. But it's there as a separate module in the historical record, notes on time series. So anybody inclined to historical research, this would be, I'm sure this would be a project that bears fruit.